Welcome to the Deep Dive. We take the sources you provide, articles, research notes, all that stuff, and, well, we boil it down to what's really important, insightful, maybe even surprising. Today, we're looking at this really comprehensive guide you shared on the fundamental physics of sound.
Right.
And we're diving into something foundational, something we experience every single day, but maybe don't think about much.
Yeah.
Sound itself.
Yeah, it's everywhere.
So our mission today is to unpack it all. You know, how sound is made, how it travels, what makes a whisper different from a shout, even how you make things soundproof.
It's going to be fascinating. Prepare to maybe hear the world a bit differently after this.
I hope so. So where do we even start? Sound is energy.
Exactly. Sound at its absolute core is a form of energy, and it's the energy that creates the sensation of hearing in our ears.
Right.
And the fundamental principle, the starting point for all sound, is vibration. Sound is produced by the vibration of objects, period.
Vibration. So every single sound, no exceptions. That leaf rustling, a car horn, my voice right now.
Every single one. It all starts with something moving back and forth, vibrating.
It's kind of wild to think that it all boils down to this tiny, maybe invisible movement. So when the physics guide talks about vibration, is it just any old movement?
Not quite. The sources distinguish between oscillatory motion, that's like a swing, back and forth, rhythmic, and vibratory motion.
Okay, what's the difference?
Vibratory motion is more specific. It's often where a part of an object vibrates, maybe really fast, while another part stays relatively fixed. Think of a guitar string.
Okay. The ends are fixed, but the middle part shakes like crazy.
Exactly. Or a drum skin, it ripples and vibrates when you hit it. That's vibratory motion. And the key thing, the absolute takeaway is every source of sound is a vibrating body.
And when it stops vibrating?
The sound stops. Simple as that.
It makes sense. You can feel it, right? Like you put your hand on your throat when you talk or sing.
You feel the vibration from your vocal cords. Perfect example.
Or, you know, that classic thing with a ruler on the edge of a desk. You twang it, it hums.
And then silence when it stops moving. Or stretching a rubber band and plucking it. Same idea.
The guide also mentioned seeing rice grains dance on a drum. That's a great visual for the vibration.
It really is. Shows you the energy transfer. And of course, musical instruments, plucking, a sitar, a guitar. It's all vibration.
So many different ways to make something vibrate.
Absolutely. The world of sound sources is incredibly diverse, stemming from that one simple principle.
And that variety really comes through when you look at things like, say, a tuning fork compared to a whole orchestra.
It does. Tuning forks are interesting, those metal U-shaped things.
Yeah.
Strike one gently, you get this pure, often quiet tone. And you can actually see the vibration if you, say, touch it to a ping pong ball hanging on a thread.
Oh, neat. What happens?
The vibrating prong just knocks the ball back and forth. It makes the invisible vibration visible in a way.
Cool. And then musical instruments are just like sophisticated vibration machines.
Pretty much. Wind instruments, flutes, clarinets, whistles, they work by making the column of air inside them vibrate when you blow.
So the air itself is vibrating.
Yes. Then you have reed instruments, harmoniums, mouth organs. They have these little metal strips, reeds.
Like tiny metal strings?
Sort of, yeah. Air blows over them, makes them vibrate, and that creates the sound.
Okay. And string instruments are obvious, I guess. Guitars, violins.
Right. Stretched strings vibrating when you pluck them or hit them like in a piano or bow them like a violin.
And drums.
Membrane instruments. You strike the membrane, the skin, and that vibration produces the sound. Drums, tablas, dolacs, that family.
And then there's us.
Humans.
We are definitely sound sources. Our vocal cords, which are in the larynx or voice box,
Right.
they vibrate when air from our lungs rushes past them. That lets us talk, shout, sing. And like you said, you can feel it right here on your throat.
Amazing. And lots of animals use the same basic idea.
Many do. Birds, frogs, they have vocal cords too.
Yeah.
But then you get interesting cases like bees. The guide mentioned them.
Oh, yeah, the buzzing. They don't have vocal cords, right?
Nope. They make that sound by beating their wings incredibly fast. It's the wing vibration itself creating the buzz.
Wow. Different mechanism entirely. Okay, so we've established vibration is step one. But how does that vibration get from, say, the bee's wing to my ear?
Propagation. This is crucial. Sound needs something to travel through. It needs a medium.
It can't travel in empty space?
Correct. It cannot travel through a vacuum. The classic experiment for this is the electric bell in a vacuum jar.
I think I remember this from school. You put a bell in a jar and pump the air out.
Exactly. You start the bell ringing, you hear it fine, then you start the vacuum pump, removing the air.
And the sound fades.
Gets fainter and fainter until you can't hear it at all, even though you can still see the little hammer hitting the gong inside. No air, no sound transmission.
Which leads to the space example. Astronauts talking on the moon.
They need radios because there's no air, no atmosphere. Sound just can't travel between them directly.
That really drives it home. And the guide suggested a home version. A phone in a glass.
Yeah, put a ringing mobile phone in a tumbler or glass. Listen to it. Then try and suck the air out from around it, maybe carefully with your mouth over the top, or using a straw sealed around the edge.
Does it work?
The sound gets noticeably quieter as you remove some of the air. It shows how much sound relies on that medium.
So the medium is essential. But it's not just air, right? Sound travels through other things.
Oh, absolutely. It travels through solids, liquids, and gases.
Solids. Like what?
Well, put your ear flat against a wooden table. If someone taps the other end very lightly, you'll hear it much more clearly through the table than through the air.
Right, right. Or the old string telephone toy.
Perfect example. 2 cans and a taut string. The sound travels along the solid string.
Okay, and liquids.
Yep. The guide suggested filling a balloon with water, holding it to your ear, and touching a ticking watch to the other side.
And you'd hear it.
Clearly. Sound travels through the water.
And gases, well, that's mostly air for us. Hearing someone call your name from across the room.
That's the most common way we experience sound travel, through the air.
So sound energy gets from A to B.
Yeah.
But if the air particles themselves aren't flying across the room, how does the energy move? You said it's a wave.
It is. It's wave motion. Think of it like dominoes falling. Each one knocks over the next, but the dominoes themselves don't travel down the line right.
Okay, good analogy.
The particles of the medium air, water, whatever, they just vibrate back and forth around their fixed positions. They bump into their neighbors, pass the energy along, and then return.
And sound is a specific type of wave.
Yes, it's a longitudinal wave. This means the particles vibrate back and forth in the same direction that the wave itself is traveling.
Like pushing and pulling a spring, a slinky.
Exactly like that. You get areas where the particles bunch up and areas where they spread out.
And those are the compressions and rarefactions mentioned in the guide.
Precisely. Compression is where the particles are squeezed together. Rarefaction is where they're spread apart. The sound wave is this series of traveling compressions and rarefactions.
Got it. So if sound is a wave, like light or water waves,
Yeah.
it must have characteristics, right?
Right.
Ways to describe it.
It does. The sources point out 4 key ones. First, wavelength. Symbol lambda.
Okay.
That's the physical length of one complete wave cycle, say from the middle of one compression to the middle of the next one.
Makes sense. What else?
Amplitude. Symbol A. This is how much the particles are displaced from their resting position, how far they move back and forth. It's basically the intensity of the vibration.
Right. Bigger swing.
Then there's time period, T. That's simply the time it takes for one full vibration or one full wave cycle to pass a point.
Okay.
And finally, frequency, F. This is maybe the most talked about one. It's the number of complete vibrations or cycles that happen in 1 second.
And that's measured in hertz.
Measured in hertz, hertz. And frequency and time period are inversely related. Frequency is just 1 divided by the time period.
Okay, frequency. That relates to pitch. Right. But before we get there, the guide mentioned something about our hearing range. We can't actually hear all frequencies.
That's right. Humans have limitations. Our audible range is generally considered to be from about 20 hertz on the low end up to 20,000 hertz or 20 kilohertz on the high end.
So anything below 20 hertz or above 20,000 hertz, we just don't hear it. It's silent to us.
Completely silent, even if the sound wave is physically there.
Wow. So what are those sounds called, the ones outside our range?
Sounds with frequencies higher than 20,000 hertz are called ultrasonic. Sometimes supersonic, but ultrasonic is more common for the frequency itself.
And we can't hear them, but some animals can.
Oh, yes. Dogs can hear up to maybe 50,000 hertz. Bats go way higher, up to 100,000 hertz or even more. Monkeys, deer, leopards, too.
And bats use it.
Yeah.
For navigation.
Exactly. It's incredible. They emit pulses of ultrasonic sound and then listen for the echoes bouncing off objects. It's like natural sonar, letting them see in total darkness.
That's amazing. Okay, so that's high frequency. What about the low end? Below 20 hertz.
Those are called infrasonic sounds, or sometimes subsonic, frequencies lower than 20 hertz.
And we can't hear those either.
Nope. The guide gives the example of a simple pendulum on a clock. It might oscillate back and forth once every 2 seconds, which is a frequency of 0.5 hertz. Way too low for us to perceive as sound.
So there could be all sorts of ultrasonic and infrasonic sounds happening around us right now that we're totally oblivious to.
Almost certainly. But one key point. The speed at which sound travels doesn't depend on whether it's audible, ultrasonic, or infrasonic. In a given medium, like air at a certain temperature, they all travel at the same speed.
Interesting. And the guide mentioned something about babies hearing higher frequencies.
Yeah, that's fascinating. Infants can apparently hear sounds up to around 35,000 hertz. That ability gradually decreases as we age, settling down to the typical 20,000 hertz limit for adults.
Huh. Makes you wonder what they're hearing that we're not. Okay, back to amplitude and frequency. How do these wave properties translate into what we actually hear, like loudness and pitch?
Right, those are the two main perceptual qualities. Loudness is directly related to the amplitude of the sound wave.
So bigger amplitude means
Louder sound. Think back to the guitar string. Pluck it gently, small vibration, small amplitude, soft sound. Pluck it really hard, it vibrates much wider, bigger amplitude, much louder sound.
same for hitting a drum harder.
Exactly. Hitting it harder transfers more energy, creates a larger amplitude vibration of the drum skin, and thus a louder sound. The dancing rice grains jump higher.
Makes sense.
And there's another factor for loudness, the area of the vibrating body. A bigger drum naturally produces a louder sound than a small one, assuming the same force because more surface area is moving the air. Same for a huge temple bell versus a tiny handbell.
Okay, so amplitude equals loudness. What about frequency?
Frequency determines pitch, how high or low a sound is perceived.
High frequency is high pitch.
High frequency means a high pitch, what we often call a shrill sound. Low frequency means a low pitch, a flat or grave sound.
Like a whistle versus a foghorn.
Perfect contrast. Or think about voices. A child's voice is generally higher pitched, shriller than an adult male's voice because their vocal cords vibrate at a higher frequency.
The guide had an experiment with test tubes and water blowing across the top.
Yes. If you have a test tube with just a little water, the air column inside is long. Below across it, you get a relatively low pitch. Add more water, the air column gets shorter.
And the sound gets higher, shriller.
Exactly. The shorter air column vibrates at a higher frequency. You hear the same effect when filling a pitcher with water. The pitch of the pouring sound rises as the water level gets higher.
So musical instruments are basically designed to control these frequencies very precisely.
Absolutely. Wind instruments change the length of that vibrating air column by opening and closing holes or using valves.
Right.
String instruments change pitch by altering the string's length, like pressing down on a fret, its tension, tuning pegs, or even its thickness.
Yeah.
Different strings on a guitar have different thicknesses and tensions.
So much control over vibration. Okay, we know sound needs a medium. We know about its wave properties. What about its speed? Does it always travel at the same speed?
Good question. No, it doesn't. We already said it needs a medium, and it definitely takes time to travel.
Like thunder and lightning, you see the flash.
Instantly, pretty much. Light is incredibly fast. But the sound, the thunder, takes noticeable time to reach you, especially if the storm is far away.
So you can estimate distance based on that delay.
You can. And people have used similar methods, like timing the sound from a distant cannon flash to measure the speed of sound in air. The guide gives the standard value as approximately 330 meters per second.
330 meters. That's fast, but not that fast compared to light. Is it faster or slower in other things, like water or steel?
Much faster in liquids and especially solids. That's a key point.
Really? How much faster?
Significantly. In water, it's around 1,500 meters per second. In steel, it's way up there, around 5,000 to 6,000 meters per second, depending on the type of steel. Iron is also over 5,000 meters.
Wow. So solid fastest, then liquid, then gas, air is the slowest.
That's the general rule, yes. Solids transmit the vibrations much more efficiently because the particles are packed closer together.
Which explains that old trick of putting your ear to a railway track to hear if a train is coming.
Exactly. You'll hear the vibrations through the steel rail long before you hear the sound traveling through the air. It's a direct consequence of sound traveling faster in solids.
The guide mentioned hearing a sound twice through a metal rod.
Yeah. If you have a long metal rod and someone taps one end while you listen at the other, you might hear a faint sound almost instantly through the metal.
And then a moment later, the sound arrives through the air.
Precisely. It demonstrates the speed difference quite clearly.
Are there other things that affect the speed, like temperature?
Yes. Temperature matters, especially in gases. In air, the speed of sound increases by about 0.61 meters per second for every 1 degree Celsius rise in temperature.
So it's faster on a hot day than a cold day.
Slightly, yes. And it also travels a bit faster in humid air than in dry air.
Interesting details. Okay, so sound travels, it has speed, pitch, loudness. What happens when it hits something? Does it just stop?
Not usually. It interacts with surfaces. The two main interactions are reflection and absorption.
Reflection, like a mirror reflects light.
Very similar principle. When sound waves hit a hard, large surface, they bounce back into the same medium.
Like shouting at a cliff face.
Exactly. And it follows the laws of reflection, just like light. The sound hits the surface, angle of incidence equals the angle it bounces off, angle of reflection.
And this is used in things like megaphones.
Yes, megaphones, speaking tubes, even the shape of some musical instruments like trumpets or horns. They use reflection to direct the sound waves in a specific direction, making them seem louder.
And the most famous example of reflection is an echo.
The echo. That's the distinct sound you hear when a reflected sound wave comes back to you from a distant object, cliff, wall, side of a large building.
But you don't always hear an echo, even if there's a wall nearby. Why is that?
Because of how our brain processes sound. There's something called the persistence of hearing. A sound needs to last in our brain for about 0.1 seconds for us to perceive it clearly. So, for you to hear the reflected sound as a separate event, as a distinct echo, it needs to arrive at your ear at least 0.1 seconds after the original sound you made.
So if the wall is too close, the reflected sound gets back too quickly.
Exactly. It arrives before that 0.1 second window closes, and it just merges with the original sound, maybe making it sound a bit muddled or prolonged. That's called reverberation.
So how far away does the wall need to be for a clear echo?
Well, if sound travels at 330 meters, in 0.1 seconds it travels 33 meters, but that's the total distance out and back.
So the actual distance to the reflector only needs to be half that.
Right. Roughly 16.5 meters, or about 54 feet. That's the minimum distance for a clear echo in air under typical conditions.
That's further than I might have guessed. Okay, so that's reflection. What about the opposite? Absorption.
Absorption is when a material basically soaks up the sound energy instead of reflecting it.
What kinds of materials do that?
Generally, soft, porous, or lightweight materials. Think sofas, thick carpets, heavy curtains, acoustic ceiling tiles, even things like paper or thermocol. Wood also absorbs some sound.
These are the things you find in places trying to control sound, like recording studios or concert halls.
Precisely. They're used to reduce echoes and reverberation, and also to stop sound from traveling through walls. Which brings us to soundproofing.
Right. The guide talked about designing a soundproof box or room.
Yeah.
How does that work based on these principles?
Well, true soundproofing is very difficult, but reducing sound transmission involves both blocking and absorbing sound. You want to stop sound getting in and stop sound getting out.
So heavy, dense materials to block.
Yes, like thick walls, but also adding absorbent materials. The guide mentioned things like using plaster of Paris over thermocol sheets and ceilings, putting acoustic tiles on walls, laying thick carpets.
And curtains.
Thick, heavy curtains absorb a lot of sound, especially higher frequencies. Sealing gaps is also critical, using thick stripping around doors and windows because sound will travel through any air gap.
Even putting noisy equipment outside the room helps.
Definitely. Things like air conditioners or even computer fans, if possible. It's about reducing the sources inside and blocking absorbing sound transmission through the boundaries.
The guide had a simple DIY version. A shoebox.
Yeah. Line a cardboard shoebox with something soft and porous bubble wrap. Egg cartons are often suggested, maybe foam. Put a ticking clock or a quiet radio inside. Close it tightly.
And you shouldn't be able to hear it from outside.
Or it should be significantly quieter. It demonstrates the principle of using absorbent materials to trap sound within an enclosure.
That's really fascinating. We've gone from the tiniest vibration causing sound.
Right up to designing concert halls and understanding echoes.
Yeah, how it travels as a wave, what pitch and loudness mean in terms of frequency and amplitude, how fast it goes in different stuff, and how it bounces off or gets soaked up by materials.
It covers a lot of ground.
It really does. This deep dive, based on that guide you shared, gives such a great shortcut to understanding something so fundamental, and some surprising details in there.
Absolutely. And, thinking about all this, how precisely frequency relates to pitch and amplitude to loudness, and how we've learned to manipulate those with instruments controlling vibrations and air columns. It leads to a final thought for you, the listener.
Yeah.
If we understand these relationships so well, how might we use that knowledge beyond just music? Could we potentially use carefully tailored sound waves, specific frequencies, specific amplitudes for completely new things, maybe in communication or perhaps even manipulating energy, or who knows, maybe even for applications in medicine? What could precisely controlled sound do?